Okay, well, good evening, ladies and gentlemen, and welcome to the November lecture. I'm very pleased this evening to be able to introduce Dr. Richard Skeffington, who's Emeritus Research Professor of Geography from the University of Reading, where he held a personal chair from 1999 till 2018. Richard's first degree was actually in biochemistry, but his interests soon changed, translated from the molecular to the workings of the environment, and his PhD was the study of physiological ecology. Afterwards, he worked for several years on heavy metals and land reclamation, and joined a research facility of a publicly owned electricity company to research the environmental effects of electricity generation and their mitigation, especially with respect to the effects on air pollution. He continued in this industry until joining the University of Reading with a personal chair in 1988, and became research professor of geography, as I said, working on measuring and modelling water pollution and climate change, water and air pollution, in terms of climate change, with running also courses both at undergraduate and master level in pollution, as well as other factors. He retired in 2018, but still has maintains an active interest in these fields. So without further ado, Richard, I'll hand it over to you.
Thank you very much. Thank you very much, Malcolm. And thank you, CSTS, for inviting me to give this lecture, and also for coming out, or rather not coming out, on this windy night to come and hear. Well, I'm going to talk about air pollution. There's lots of fascinating stories, scientific stories in air pollution, but what I'm going to concentrate on tonight is air pollution and health. And be bombarded with headlines all the time about air pollution and health, a few relatively semi-random ones coming up on the screen. 15 million Britons exposed to toxic levels, rises in depression. Air pollution cuts people's lives by an average of 6 months. Indoor and outdoor air pollution claiming at least 40,000 UK lives per year. And it's these last two that I want to devote this lecture. Really 40,000 of us dying from air pollution every year? And if so, what's killing us? And what can we do about it? Well, I think as we go through, you'll see that it's maybe not quite so cut and dried as the press sometimes makes it out to be. Well, UK is not the only country that's bothered about air pollution, and for a long time. The United Nations has been doing a study called the Global Burden of Disease, which tries to work out what diseases are killing who and where, and secondly, what's causing those diseases, including air pollution. And air pollution is actually the 5th of the commonest cause after, I think, obesity and factors like that. So if we look at the map of the world, this is 1990, and the figures I've added to it show the percentage of deaths which are due to air pollution. In 1990, it was 6.6 in the UK, substantially better than in China and North Korea, where it was almost a quarter of deaths. And if you wanted not to die from air pollution, then this map anyway, Finland is the best place to be. Move on 20 years to latest figures, and you can see that the figure's gone down quite a lot, 2.4%. North Korea's got even worse. Other countries have got worse, India, Bangladesh, Nepal, and this is largely because of increasing prosperity has led to increasing traffic. China has come down, which might surprise you, but the Chinese had a big effort at reducing pollution over the last decade. If you're good at arithmetic, you'll probably be able to work out that 2.4% of UK deaths, which are about 600,000 a year, is not 40,000, but more like 14,400. So the UN doesn't think as many people as dying in the UK, and you'll find out by the end of the lecture why not. Okay, so what I want to cover is air pollution getting better or is it getting worse? Where do these estimates of health effects come from? How good are they? What's responsible for them? What can we do about them? And as it's inextricably tied up with politics, what are the political obstacles to doing better than we're doing? And finally, since we can't ignore the current crisis, it's been quite useful for pollution scientists. Lockdown reduced emissions quite a bit. What happened? Just do a brief piece on that. And then, does actually air pollution have any effect on whether we get infected by the deadly virus or not? So quite a lot. Last time I gave a public lecture, I got accused of using too many graphs. So I hope this audience will be comfortable with a few graphs. Well, before we get to the present today, just a quick look at some history, because history tells you something. And I'd just like to take you back for 320 years. So William and Mary had just ascended the throne, and a physician called John Gadbury was about to do a bit of pioneering air pollution research. It's November, and this week in November, 320 years ago, you will see there are 6 foggy days in London. And moreover, 2 of them were labelled by Gadbury as thick, stinking fogs. In fact, most weeks had at least 1 foggy day. Now, London had very good data on deaths through what were called bills and mortality. The parishes kept very good records of who died. And what Gadbury noticed was that after the thick, stinking fogs, there was a huge peak in deaths in London, more than double. He recorded separately just deaths from something called T-sick, which is probably TB, but we can't be totally sure. One thing you can notice here, there was a big death after the first thick, stinking fog. After the second thick, stinking fog in December, there wasn't much effect. And this is something that's been seen time and time again, and it's rather charmingly known as the harvesting effect. So what happens is that people who are susceptible get caught by the first wave. By the time the second wave comes along, then the population is in general more resistant. And you could see just the same thing as the first wave of the COVID virus came down, and the death rate fell down below the long-term. Well, moving forward 300 odd years to when I, and I guess much of the audience, were growing up in the UK, things didn't seem to have improved very much. Indeed, they got worse due to the Industrial Revolution, a typical townscape in the 1950s showing lots of domestic coal burning, factory chimneys, a grey, murky atmosphere. And the famous photographer called Bert Harvey had recorded what things were like in Leicester in the 40s and 50s. So 1948, we have a grey town, no cars, you'll notice, smoking chimneys, and you can't see the end of the street. By 1954, well, we had some teddy boys, 1 car, you still can't see the end of the street. Things didn't change very much, and they didn't change because the government didn't want to spend money on pollution control. And what changed things was, as I expect, well, let's just let's just have a look at some scenes of the time. These are a couple of clips from the sort of newsreels that were shown in cinemas, like Pathé News, although they're not actually Pathé News. And you can see that the commentaries were meant to give the impression that, you know, well, it was a bit awkward, but we Brits would carry on, we'd be okay.
Detonators laid on the rail signal the approach of oncoming trains. Despite everything, they still go.
So watching playing football could be a challenge, to be a referee especially, or a goalkeeper, this sort of condition. See the crowd on the left. So what changed things? Well, as I expect you know, what changed things was the Great London Smog of December 1952. And it was anticyclone, stable air, near freezing weather. The average visibility in central London was more than 4 days. Sort of thing you don't see anymore. Then it wasn't quite routine, but it did happen periodically. Here's a famous diagram showing the effect of the Great Smog. But here's smoke, sulfur dioxide going up to high levels to micrograms, no, milligrams. Right. And shortly after the smoke and SO2 go up, then the deaths go soaring up. And if you calculate the excess deaths over and above what's normally at that time of year, it killed about 4,000 people, or did it? And no one was expecting these extra deaths because the occupational limit for sulfur dioxide, which was supposed to be safe to spend your whole working day in, was 13 milligrams per cubic meter on the scale on the right-hand side of the graph. In other words, it was about 3 times higher. What seems to have done it was it's the combination of sulfur dioxide and particles that was so dangerous, 2 pollutants together, bringing things down deep into the lung. So deaths remained high for many weeks. Here we can see the graph extended out to March. This is what we just were looking at in the last slide. Deaths go up, go down a bit, but then they go up again. Now, the government explained these extra deaths by an influenza epidemic, but in the year 2002, epidemiologist called Deborah Davis suggested that this influenza epidemic had been made up by the government, and in fact that we ought to attribute these extra deaths to the pollution event as well. That would take it up to 12,000 deaths. This distance in time, it's impossible to tell whether this is a valid claim or not, but to some extent, 4,000 or 12,000, that's a lot of people to die from a single pollutant event. Well, this gave a big impetus to change. Someone once said that it was lucky this happened in London, because if it had been the Great Barnsley Smog, then nothing would have happened, because what do you expect if you live in Barnsley? So this led ultimately to the Clean Air Act of 1956, but the government needed quite a bit more shoving. And the guy who gave it the shove was this man, you remember him, Gerald Navarro, MP, popularizer of the personalised number plate, but also the man who, to the government's horror, won the ballot for private members' bills and set out to provide a cross-party support for a Clean Air Act. And he got so much support, the government gave in and said, well, withdraw your bill and we'll make a Clean Air Act. So hence the Clean Air Act, 1956, which improved things quite rapidly. So quite rapidly, but not rapidly enough for some people. So growing up, as I did, in a small town in Lancashire, my grandfather had lived there his whole life. He and his friends never got to my sort of age, 71. They actually died in their late 60s. The vast majority of older people had chronic bronchitis, the buses all had big notices saying no spitting, and and this was essentially due to indoor and outdoor pollution. So things improved. So the next graph shows the emissions of major pollutants since 1970, and this is almost a social history of Britain. You can get immediately the impression things are all related. If we call 1970 values 100, then these are the values in. For instance, sulfur dioxide goes down and down till at the end it's only 2% what it was at the beginning, and it had already come down quite a lot due to the Clean Air Act. VOCs, volatile organic compounds, did nothing very much for a minute, but then they were caught by various EU directives. If you buy tins of paint now, you'll see they've all got diagrams of volatiles on them, and there's big pressure to reduce the amount of volatiles that brought it down. Nitrogen oxides came down here, and essentially due to fitting catalytic converters on cars and power stations improving their control of nitrogen oxide. Ammonia, slightly different pollutant. It's produced mostly from agriculture. And here it's really the differences in the number of livestock. Pigs went down there a bit. Dairy cows are going up, so ammonia is coming up again. And finally, PM, particulate matter. Again, it's mostly gone down because of the reduction in burning coal. See this illustrated neatly here. It's a little dip in 1984. This was the miners' strike when there was less coal burn, and it affected, apart from ammonia, all the pollutants. So it looks good, but it looks less rosy if you look in more detail. Particularly, there's not been a great deal of progress since 2010, apart from in SO2. and particularly in particulates seem to have stalled and started going up again. There are reasons for that, which we'll come to in a minute. So emissions and concentrations have declined, but they are still affecting our health. I just want to concentrate on the two of the major pollutants that are, and that's NOx and particulate. So NOx, what is it? Well, it's a mixture of two nitrogen oxides, nitric oxide, NO, and nitrogen dioxide, NO2. They are just added together and called NOx. And they're treated together because they interconvert in the atmosphere. This little rather simplified cycle here shows that NOx, NO will be oxidized. Atmospheric oxygen will oxidize it, but ozone, O3, oxidizes it more rapidly to NO2. And in turn, NO2 is decomposed by UV light back to NO and indirectly ozone again. So this cycle's going on in the atmosphere. Where does the NOx comes from? Well, about half of it, this side here, comes from transport. So if you want to do anything about transport, about NOx, you have to tackle transport. This cars is the major individual component. Surprise, it's this little heavy vehicles. These things are off-road transport, rail, diesel rail, and also aviation, but only in the bottom 2,000 meters of the atmosphere. Now, what happens when these gases get into the atmosphere? Because this has big implications for health effects. So this shows a recording, a continuous recording of the concentrations of three pollutants. NO in black, NO2 in green, and ozone in blue. As a site that's familiar to me in Cemetery Junction in Reading. You've seen the Ricky Gervais film, it's the same place. Cemeteries are a good place for air pollution monitoring, not much disturbance. What you can see is there's daily cycle. And the daily cycle of NO is essentially the cycle of traffic. So on the 23rd of March, there's the morning rush hour, there's a peak of NO. Then if you think back to that diagram, then what you then see is the NO reacts with ozone and it pulls the ozone right down to almost zero in this case and produces NO2 in green, the NO2 going up. And during the day, the ozone gets regenerated because these are sunny days. The ozone is produced by UV lighting in sunlight. So the ozone goes back up and the NO goes back down. And this is repeated on a daily basis. Come the weekend, less traffic. And by this time, we were into lockdown, so even less traffic. The ozone is more or less unaffected. So the atmospheres are just a huge chemical reactor. And these gases are just going up and down all the time. Other things than what I mentioned are happening. So it's very difficult really to work out if you have health effects, what has caused it, all these things. So passing that. But one thing you can do is you can do some experiments. You can ask some volunteers to sit in a chamber and get fumigated with pollutant. So here they are, and this is at a facility at the University of Umeå in Sweden. And these are very often medical students because they're interested in effects of the body. And these couple of slides are courtesy of Professor Frank Kelly at Imperial College. And these, you can fumigate them with gases, and then afterwards you take them out. You can do bronchoscopy, putting tubes down their lungs. You can take biopsy samples to see if anything's happened to them. You see if they're coughing excessively, and so on and so on. So, okay. So the annual mean guideline value, the value that we're always trying to meet, the value the government gets criticised for not meeting, is 14 micrograms per cubic metre. So what happens if you expose these people to 40 grams per cubic metre for a day, say? Well, if they're young, healthy adults, the answer is nothing. There's no coughing, they can't see anything through bronchoscopy. But some people are much more sensitive to pollution, asthmatics, for instance. What happens to them? Well, if it's 40 micrograms per cubic metre, the answer is still nothing. To get an effect in a short time, you need about 2,000 micrograms per cubic metre. For healthy adults, for asthmatics, about 400. So this gives you a basis for a short-term pollution standard. You divide the 400 by 2. It's a sort of engineering approach. Give you precautionary reasons, which gives you a value of 200, which is the current guidelines for the UK, EU, WHO, etc. And so over an hour, you can't exceed 200 micrograms per cubic metre more than 80 times a year. Why 18? Well, it's just a realization, probably it's impossible not to have an occasional episode of very high NOx due to meteorology or whatever. And 18 was chosen as to be a value that was achievable, but which would just motivate a bit of improvement chance. So, although people often think that standards are things above which it's devastation and below which you're safe, this isn't really the case. There's always some uncertainty, and there's always things like this, which are there just, there's an interaction with achievability as well. Okay, so what's the annual mean? What's the 14 micrograms per cubic metre based on? Can't really expect even medical students to stay in this box for a whole year. So what it's based on is something that we've heard a lot about recently, namely epidemiology. So I just want to explain how it's done. And to do this, I'm going to switch pollutants to particles because it's easier to explain with particles. So particulate matter, PM. Pollution scientists are concerned with how big it is. See why in a minute. But there's PM10, which is 10 micrometers or less. And this little graphic from the US EPA shows what the size of this is compared to a human hair. Small, the blue spheres are PM10. And then smaller still, 2.5 micrometers, so 4 of them fit into a blue sphere, which is PM 2.5. Got to know what the virus looks like compared to this. It's about 0.1 in these units, so you get 25 viruses across one of these red spheres. So small particle. And the reason size matters is it affects how deep it gets into your lung. So diagram of the lungs. If it's more than 10 micrometers, your nose pretty well filters it out. Between 10 and 2.5, it gets down into the bronchi, the tubes down here. But once again, there's a system, there's mucus, which is constantly being wafted up by little hairs up into your throat, which you then swallow, which takes out particles. If it's less than 2.5, the particles can get right down into the gas exchange stacks, the alveoli right at the bottom. Even finer particles might even be absorbed into the blood. So therefore, these are the dangerous particles, the ones that can get really deep into your lung. Just to note, say these cutoffs are not absolutely, the lung is not perfect at filtering all these things out. Where does the PM10 come from in the UK? Well, you can see that 44% of it actually comes from our old friend domestic combustion in domestic fires. And the reason it's so big is that very stupidly, the government a few years ago allowed wood burning stoves to be operated in smoke control areas in cities. 87% of this actually comes from wood burning stoves. So this has set back the sort of particulates to back about 30 years. So we're back here to about the levels we were in 1990, and it's the reason why particulate matter is creeping up. However, to say this doesn't include particulate matter, which is generated by chemical reactions in the atmosphere, or particulate matter that comes in from outside the UK. Both these are substandard. Well, what do these fine particles do to you? And this is the title page of a landmark paper from the New England Journal of Medicine by Douglas Dockery and colleagues about the Harvard 6 City Study, which was begun in 1974, specifically to look at the effects of air pollution on people's health. And it's what's called a prospective cohort study. What this means is you pick a group of people, about 1,500 in their cases, in each of these cities, try and match them up as far as possible for age, gender, smoking habits, etc., etc. And then you watch them and you see how long they take to die or what illnesses they get on the way. So in this paper, what we see is a graph of survival in each of the 6 cities, which shows the percentage surviving year by year for 14, 16 years. These are the cities. They're only cities in the American sense. They're mostly pretty small places apart from St. Louis. So they're only once a city in our sense. But they were chosen to give a range of pollutant concentrations. So Steubenville is in the Ohio Valley, the big coal burning area. St. Louis, the big city on the Missouri. These two are out in Wisconsin. They're away from Harvard, but it's meant to be clean air area. And you can see just at the end there, I've just detailed how many deaths per 10,000 this would mean after 14 years. So if you are in Topeka or Portage, you might expect about 1,200 deaths out of 10,000 people. If you're in St. Louis or Steubenville, it was more like 2,100, almost twice as many. So something was affecting people there, and what was it? Well, this graph shows each city represented by a letter, so this is Steubenville, etc., relative to the clean air site of Portage, which is given a value of 1, and relative to pollutant concentration along this axis here. And you can see in some cases it doesn't match very well. So aerosol acidity doesn't match. Sulfur dioxide doesn't match too well. What matches really well is the concentration of fine particles and sulfate particles, which are also tend to be fine particles. So this was the first intimation really that fine particles were very, very important and could show a very strong relationship to human health. And of course, an enormous amount of controversy. And people pointed out that problems with the study, like there was one measuring site per place. And for instance, what you put on this axis, the pollutant concentration axis, when pollutants over the 14 years had actually been declining quite strongly, was the effects actually due to before this study even started, so where people were exposed to even higher concentrations as they were in this country. So this sparked off an enormous amount of work around the world. One thing you can do, though, is another type of immunological study called a cross-sectional study, where you take a lot of cities, a lot of places, and just look at short-term mortality compared to pollution concentration. So each dot is a city. Here we've got the pollutant concentrations in the middle of the time the study was done. And you can see, once again, PM 2.5 has a good relation to mortality. Sulfate particles, this was measured more often in those days, so there are more points. Again, a good relation, but total particles, which includes the bigger stuff, although there's a line drawn through it, there is actually no correlation at all. Well, numerous studies of this sort have been done, and the results are really very consistent. And I just summarize them in this final one. So this is based on 41 studies in 16 countries. And the two graphs show on the top the overall effect, and on the bottom, the effect on different diseases. And what it's plotted against here is called the hazard ratio. What this means is it's 1.2. It means you're 20% more likely to die in this case than people who are not exposed to the pollutant at all. So the bottom graph is for 60 to 64-year-olds, and therefore the hazard ratios are higher than they are for the population in general. It also shows the relationship with different diseases. And LRI, lower respiratory tract infection, as you might expect, does show a strong influence with the particles. But the green line is ischemic heart disease. That's the normal heart attacks, cardiac malfunctions of that sort due to narrowing arteries. So it's not just the lungs, it's the whole cardiovascular system that seems to be affected by the particle. And with a slightly lower slope, we get lung cancers, we get strokes, and we get COPD, what we would have called chronic bronchitis. So if we want to know where we are on this graph, so this is the PM values for the UK mean in 2010 by current time it's gone down slightly. This gives you a hazard ratio in general of about 1.06. Other places, China, for instance, would give you a hazard ratio of about 1.5. In other words, you're 50% more likely to die. Chinese has had a big push at reducing particulates. That's why they improved in the graphs I showed at the beginning. And so, therefore, you come down this line, reduce your hazard. Note, here there's a threshold. What they're saying is below 2.4 micrograms per cubic meter, nothing happens. But this is controversial. And the consensus is that there isn't a threshold and that any particles are actually dangerous. Okay, so how this is where we get to the 20,000 deaths. What are the UK deaths due to particle? Well, the government has got various expert advisory committees, including the Committee on Medical Effects of Air Pollution, or COMEAP. And they did a calculation for model effects of 2.5. So I'm not going to go through their calculation because you can do it rather more easily. What you say is, well, they said there's a relative risk is 1.06. In other words, you're 6% more likely to die for a 10 microgram per cubic meter increase in PM2.5. They also worked out a confidence limit. Notice this is pretty wide. So the mean is about 600,000 deaths a year. So 6% of that is about 29,000 deaths due to particle in the UK every year. If you add the confidence limits, this is takes you to 5,000 to 60,000. If you use the confidence limits, these are not 95% confidence limits, they're 75% confidence limits. So in fact, the probability that the value is actually outside this range is about 1 in 4. So there's a lot of uncertainty. And even that assumes that COMEAP's done its statistics correctly. However, these 29,000 deaths are not 29,000 individuals who died from air pollution. It's not that 29,000 people died from air pollution and the rest of us were okay. You won't find air pollution on anybody's death certificate. What they mean is that these, they call are attributable deaths, which are equivalent to 29,000 deaths. Now, this concept is too subtle for most people, and especially people in press. But let's just try and tease it out a bit and see what it means. So if you multiply up 29,000 deaths into terms of life years, in other words, one life year is one person living for a year, this amounts to the loss of 340,000 life years every year. So you can spread this loss 340,000 life years across in various ways. So for the adult population as a whole, it has to be the adult population because the studies were done on adults. It amounts to everyone losing 15 minutes a day to air pollution, or 3 days a year, or 7 months during your lifetime. Again, with wide confidence intervals of 1 to 14 months. Or, well, you could say, well, really, PM2.5 is only affecting people who've got heart disease. So let's restrict it to the people who have heart disease. Do that calculation, then for people with heart disease, it means losing an average of 2 years of life each. Again, between 4 months and 4 years as a confidence interval. And this, of course, is only an average, and quite apart from the confidence interval, individuals, it may be much more or much less. Now, David Spiegelhalter, whose reasoning I followed over the last couple of slides, suggested more innovative ways to compare with other risks. So the average UK particulate is equivalent to putting on half a stone if you're already a bit overweight, watching TV for an extra hour. You might not think watching TV is all that dangerous, but actually it correlates extremely well with some deleterious health issues like diabetes and atherosclerosis. This is where the sitcom The Royal Family tends to come to mind. But, or it's equivalent to smoking about a cigarette a day. Smoking 20 a day gives you a relative risk of about 2. So for 1.06, it's just over 1. If you live, say, in Delhi, then the risk of pollution is equivalent to smoking a pack of 20 a day. But well, this is all assuming that it's compared to a baseline of 0, and the baseline of 0 is something we can never get to because there are natural sources as well as residual contribution. The lowest values are around 2. North of Scotland, it's about 2.6. You want to know where it is, where you live, Cirencester? It's 8.57 currently. Where I live in rural Wiltshire, it's a little bit lower, 7.95. And these are all below the WHO global target of 10, and which puts us in a better place than more than 95% of the world's population. The national target, which is even higher, which the national EU target is 25. But other people have worked out this sort of thing, and this shows a couple of maps. Incidentally, it just shows the effects of pollution control. So this shows the losses in life expectancy due to PM 2.5 in the year 2000. And the UK then, it was between 6 and 9 months. But we weren't as bad as some places, the industrial areas of Europe, and particularly the Netherlands, up to 3 years, life would be lost. Then this is a prediction of what it would be like in 2020, maybe about 2004, but it's more or less correct. This is based on the EU's strategy Clean Air for Europe. And now, as we just calculated, it's between 4 and 6 months in the UK and considerably less everywhere. In the Netherlands, it's still over a year. And why is it so dangerous in the Netherlands? Well, the answer is pigs. Pigs, as I indicated earlier, give off ammonia. The ammonia reacts in the atmosphere with the NOx and with sulfur dioxide to form very fine particles, the most dangerous particles. And this is enough to give the Netherlands substantial health effects, even though they have very stringent requirements for housing their pigs. Well, Public Health England worked it out, deaths on a local scale for every local authority. So if you live in the Cotswold District Council area, in 2010, you would lose, on average, 5 months and 20 days of your life due to PM10. Move down the road to Swindon, and it's about 7 months and 25 days. So, so you gain 2 months of life by living in the Cotswolds. This is just due to PM10 and the other factors, even factors going the other way. Though. Can't really think of any. Less likely to be trampled by a cow in Swindon, I suppose. But but it shows that this sort of thing can be done. And it's not just deaths, deleterious effects other than deaths can be done. And in 2010, then the Royal Society of Physicians worked out that there were 26 extra cases of chronic bronchitis, over 100,000 cases of bronchitis in children, 16,000 hospital admissions, 1.2 million asthma days with children, 6 million lost working days, and an economic cost of 20 to 56 billion pounds from air pollution, mostly particulate. And this report, Every Breath We Take, is also the source of the 40,000 deaths figure. 29,000 from particulate matter, as we just seen. You do the same thing with NOx, it comes to 23,500. Now, if you're good at arithmetic, you'll know that adding these two together doesn't give 40,000. But there's clearly some overlap. If you think of these as deaths, there's one death that's been influenced by both people. How much overlap? Nobody has much idea, really. So the Royal College of Physicians just plumped for a figure somewhere in between. DEFRA, when they came to do it, came up with something slightly higher, but everyone's stuck with 40,000. A nice round number. Well, let's go back to NOx. So NOx, as I said, it's the sum of NO and NO2, but the two gases are actually very different. NO is probably benign, and I'll just run through some of the evidence for this. We only say probably because it's impossible to expose people just to NO. See what happens. The presence of oxygen, it turns into NOx, so you do need the presence of oxygen, otherwise your fumigated volunteers will die very quickly. So you can't do experiments with it. You can't do epidemiology because the two are just so too thoroughly mixed up. But what you can do is note that we actually produce NO ourselves as part of our metabolism. And this, and it's also used in medicine in therapeutic doses. The doses that are used are enormous, like 38 to 76,000 micrograms per cubic meter for premature babies. And they're exposed to it for days. These are very sick babies, but all the same. This is vastly higher than the 200, which is the outdoor limit, the NO2. Now, NO's got a nice connection with Alfred Nobel, the inventor of the Nobel Prize winners. He made his money from making the explosive nitroglycerine safe to handle. But nitroglycerin has long been a drug used for people with angina, heart conditions, right, who had the thought that an explosive would be good for angina, but it is still used. But the reason it works, and in fact Nobel was quite amused to find himself being prescribed the explosive that made his fortune for his angina, and he refused to have it. But he didn't actually die of a heart attack, which would have been neat, but in fact he did die of a stroke a bit later. But it was known that nitroglycerin actually worked by releasing NO, but in 1986 it was realized that NO, a gas, is actually a hormone. It's released by a variety of tissues, and what things it does is cause your blood vessels to dilate, but it also affects nervous pathways, it kills things in the blood, it can kill cancer cells, it's the mode of action of Viagra. It's a very important molecule. And just in a neat little twist, so 3 scientists were awarded the Nobel Prize for discovering the effects of NO. Now, as I said, we all emit NO. This is probably accidental, but we've got about 20 micrograms per cubic meters of NO in our breath. Just for the purpose of this lecture, I just wondered, well, what does this compare to a car? So, so I did a few calculations. Well, it's actually quite small. If you've got uncontrolled asthma, you've got more NO in your breath. This can be used in the diagnosis. But supposing you haven't, and supposing there's 100 people in the Royal College of Agriculture listening to a lecture for an hour, then the amount of NO they produce will be about the same as a car traveling for 11 minutes. So not very much, but nevertheless it is. So NO is probably benign, it probably doesn't do much. But NO2 is decidedly not. And you can go through similar calculations to what I did for PM. I'm not going to do it. You'd be relieved to know to come up again with a hazard ratio. It's lower, 0.23% per 10 micrograms per cubic meter this time. And the attributable death figure is also 23,500. However, there's a catch. Experts actually disagree about the health effects of NO2 because although there appear to be effects of NO2, how much of this effect is actually due to NO2 rather than something correlated with That's the problem with all epidemiological studies. It's called confounding. So it may actually not be NO2, or it may only be partly NO2 that's causing these perceived effects. And the latest report from COMIAP, rather unusually, they had a row, and there were 3 dissenting members of the committee who didn't believe there's enough evidence to link long-term NO2 exposure to mortality. And they strongly disagreed with extrapolating effects below the observed day, whereas the rest of the committee were going to do that. There's a bit of an impasse at the moment. And it's a bit awkward because actually there's a lot of efforts being devoted to reducing NO2. But I'll just show you some epidemiological study that may support reducing NO2. So this is again from Frank Kelly. A year or 2 ago, they did a study of schools on the east side of London. Here's London. The lines are NO2 emissions, the redness, and the scale is there. And what they did was they looked at the lung capacity, the FVC of children who are living in different places. This red line here is the standard. Every, this is the children down here, going up to very high levels, most of them living above the annual concentration limit. Even children who were just below were on average losing a bit, 5.5% of lung volume. If you were living above, you were losing more lung volume. And these losses were permanent. They're not likely to be made up. So it's clear that something is damaging the lungs of these children. So the argument is it not reasonable to reduce NO2, even though we don't know for sure it's NO2? No one thinks it's all NO2. No one thinks NO2 isn't involved at all. But maybe if we reduce NO2, we'll reduce the other things that we're doing this as well. Well, just a little look at NO2 around the country. This is a map of NO2 emissions. You can see it's very close to being a road map. You see the M25 coming out very clearly, the M1, etc. We blew up the area around Cirencester, shown by an arrow. Again, you can see the roads, Swindon down here, Bristol, Gloucester. The geographers are very well aware that you can manipulate maps by choosing a judicious legend. Here, the orange covers a huge range of values, so it is giving the impression that the motorways and M4 down here are producing about as much as the main roads. This isn't the case. The amount of NO2 is much bigger. It depends on traffic density. So a better choice of legend would have shown that up. See also the railway along here now being electrified. Those emissions will go. Another interesting fact about NO is, well, we don't keep much of it, although it does things in the UK, and we produced in 2017 271,000 tonnes of it, but we only kept 41,000 of it. We exported the rest of it, 230,000 of it left the country in the air. Where did it go? Well, everywhere, essentially, all around the world, but 70,000 tonnes of it fell on other EU countries. Conversely, they gave us 16,700 tonnes back. The difference is largely because the prevailing wind blows that way, but it goes further afield still. So just as an example, 8,300 tonnes of nitrogen from our emissions fell on Russia. This is just Russia west of the Ural. So putting it another way, we're giving them 8,000 tonnes of nitrogen fertilizer, mostly in places where they don't want it, but just shows the scale of things, and also that these things need to be tackled on an international scale. Single country tackling a great deal. Another illustration of this, I'll just show you a dynamic model of NOx emissions by using the French model IMER. It's a global model that I'm just going to show Europe. The red values here are NOx emissions, and this is the French risk assessment organisation in Aries. So if we just run, this doesn't have a sound, so we'll just stop it from time to time, see what we can see. Okay, so see for one thing, what today is 5 o'clock in the evening, January. Then London, the great northern cities are producing their NOx. See other places there, the North Sea oil rigs are producing some. Wind changes, shifts direction. Do that. Let's stop again. So here we go. Wind shifts direction. Hit the target this time. So here we see Paris, sort of spreading its NOx plume right over the Netherlands and other kind of places as well. Berlin down there, Prague. NOx goes a long way. Well, up in the north of Scotland, things are nice and free. And here, the Po Valley, you see it stays high all the time, a notorious pollution hotspot. And just at the end, we see here, oh, there we go. Tongue of cold air trying to push its way down from Russia. Cold, clean air. The NOx gets everywhere. It's not just confined to the UK. Let's just move on to a global scale. So COVID's reduced global carbon dioxide emissions. So this is a good thing, but has it reduced the inexorable rise of carbon dioxide? Well, not so far. So these are monthly figures of carbon dioxide measured on Mauna Loa in Hawaii. The black line is the seasonal lines. So it goes down when we get photosynthesis, pulling CO2 out of the winter and the spring. So not much, we've had the COVID, we've had the reduction in CO2 from then onwards, not much discernible effect. But if you do the calculations, you wouldn't expect very much yet, because this cycle is very much bigger than what we produced ourselves. There's also other sources like fires in the Amazon. Well, doing something about air pollution. Can we do anything about it? Well, just last week, we got some hopeful news from London. So, Sadiq Khan has made quite a thing about air pollution. He introduced the ultra-low emission zone in the centre of London. And then before that, something called the T-charge, T for toxicity, charging polluting vehicles to go into the centre. And this shows the effect of that we can see. This is NO2, this is the standard down here. In central London, well, floods along for years and years, but the start of these has come right down, almost to the 40 microgram. Without, it was going down anyway, without, this is the model, without the ULEZ, it would have gone down, but not so much. And probably even better, the schools in areas that exceed the limit, there were 455 of them in 2016. Now there's only 14. So, I'm looking at London as a whole, 2016, anything that's reddish or yellowish exceeds the limit, or central area around the roads. Now it's much more confined. So it can be done if you've got sufficient determination. Now, have we got another 5 minutes or so, Richard? Is that okay? Yes. Nod your head if you mean yes.
Yes, I think that's fine. We're
okay.
Keeping going.
Just a bit about technology, because this is a technology society. So one thing that's dropped NOx is emission standards, and these show EU emission standards over the years, 92 down to the different numbers, Euro 1, 2, 3, 4, down to Euro 6 in 2014 for diesel in blue and petrol in red. You can see that petrol went down first because it's easier, because diesels, unfortunately, the engine chemistry is such that catalytic converters don't produce NOx, whereas petrol they do. To get down to the better levels, the Euro 6 levels, certainly you need other technology, and if you bought a diesel recently, you'll probably also have to play around with AdBlue, which AdBlue is essentially urea. It's stuck into the exhaust, it decomposes to ammonia, and this reacts with the NOx to form atmospheric nitrogen. Don't supply ammonia because ammonia is quite toxic. It's not the sort of thing you want in your car, especially in an accident. PM10, they didn't bother with standards for petrol cars because they thought they didn't have produce much PM10. But now it's down to a very low level. There's also a standard for particulate numbers because PM 2.5, because individual particles don't weigh very much. Then you can still get a lot of numbers. Standard is or was 600 billion particles per kilometer driven. So you're producing a lot of particles, you drive your diesel, and the way to get down below this, among other things, is to have a particulate filter. So there is technology, but here we come to a rather nefarious episode. Vehicle emissions vehicles are all tested against these standards in the EU, and to do this, until recently they've used something called a new European drive cycle, even though it wasn't actually very new, which essentially you put your car on a rolling road and you drove it according to this protocol. So you had you speeded up from 0 to about 15 kilometers an hour and slowed down, and then did it again. And then you had one where you actually just about got it the same at the end. So vehicles had all got to comply with it. Now it's been known this isn't terribly realistic simulation of normal driving. Secondly, the manufacturers adjusted their engines to meet the test standard. And when tackled with this, manufacturers said, well, we know what you expect us to reduce it to meet. You know, if it's got to pass this test, you're setting the test. So, and the idea was, okay, this can't possibly represent all driving conditions, but if it was good in these conditions, hopefully it would be good in all conditions as well. Well, okay, but Volkswagen did something that blew this out of the water. And what they did was they used their engine management system to detect when this test was being done. They adjusted the engine to meet the test requirements. But when out on the open road, these adjustments weren't made. Effectively on the road, it's a totally different engine. So, and the UK government's expert committees were well aware that there was a lot more NOx in the urban atmosphere than there should have been given emission factors. And they suggested to the government they should change the emission factors, make it more realistic. The government, this was the coalition government, said, well, we appreciate that's scientifically justifiable, but that would put us at a disadvantage compared to other EU countries who are not using these emission factors, so we're not going to do it. So it was left to an American charity called the International Council on Clean Transportation to reveal what Volkswagen had done. And this just shows one of their graphics showing the 3, 4, and 5 Euro standards. The test cycle emissions are the dotted line, and the black clouds are the real emissions. So for petrol, it was a bit more for Euro 3 and Euro 4, but pretty close to Euro 5. For diesel, the test cycle emissions went down, but the real emissions hardly went down at all. And by the end, the diesels were producing 16 times as much. And this is not just Volkswagen. In fact, Volkswagen's independent tests generally come out much better than the average car share, showing that it was a piece of stupidity to attempt to deceive people because they got hit by massive fines in the USA lawsuits. And there are lawsuits going on in this country as well. So now there's a new test cycle, and now there's much more stringent controls on diesel. But possibly it's too late for diesels. They've got the bad reputation. And finally, lockdown. Lockdown reduced traffic enormously. The first lockdown, it's not doing in this one, I noticed. What effect did it have? Well, some places, this is Symmetry Junction in Reading again, it's not really very obvious. Here's NO2, this is the lockdown period. It's vaguely going down, but then it normally goes down as we go into the summer anyway. To see an effect, you need to look in a more sophisticated way, and I've got this from Gary Fuller from the London Air Network. And this is the average daily concentrations of NO2 in central London. So this is before lockdown. We see low in the nights, goes up during rush hour, stays high, comes down again. Lockdown, you get the same pattern, much less traffic, but much less NO2. Then as lockdown gradually relaxed, then it went back towards what it was, but it never quite got there. And this is thought to be because congestion is still quite a lot less than it was. How this didn't apply everywhere, it's the same graph as the Burnham London site. This is much like what you see in Reading. So same colours, lockdown reduced it a bit, but now it's gone back to where it was. This is still being chewed over by the experts. The second question, does air pollution contribute to COVID-19 deaths? Early on in the pandemic, there were suggestions that it did. There's a correlation. Areas that are badly infected in Italy are also areas badly affected by air pollution. But again, confounding rears its ugly, ugly head. The factors that make COVID susceptible to COVID, particularly social deprivation factors, are very similar to the ones that make you susceptible to air pollution. However, just last week, there is a study I'll show in a moment, just to remind me, you can detect the virus on particles. Is this significant? Nobody knows, quite possibly not. Just last week, the same group, not the same people that gave you the Harvard 6 City study, published something that shows that there is a relationship between PM2.5 COVID infection and the population basis. And you can use statistical techniques to say 1 microgram increase, not much, raises the death rate by about 11%. This is in trying to adjust for confounders like age, sex, etc. This is on a county basis, so it's not applied to individual. And other things affecting COVID, these are the things we see here as well: population density, household income, educational level, and over there, percent of Black residents. Okay, so well, I hope that's giving you an introduction, at least, to air production and health. It's just a wrap up. It's much less than what it used to be, but I think we could still benefit from further reduction. You should be careful if you're making a policy with an eye on the headlines. It would be more sensible to concentrate on PM 2.5, but we're not, because it's the NOx is the standard that we're exceeding. And of course, there's still lots of things to find out about air pollution. So thank you very much.
Richard, thank you very much for that fascinating talk. I'm delighted, Richard, to know that you're recording that, because I started making notes, but I stopped making notes quite quickly with the huge number of fascinating graphs and data that you provided. If I may start off by just asking one question, which sprang to mind, and that is that I've read in various sources that another source of pollution is from tyres, that quite a lot of particulate particles effectively are flung into the air by cars and huge amounts of traffic. Can you make any comment on that?
Yes, what sort of fires are we talking
Well,
about?
all cars, I think, I don't know at all. I mean, it has been mentioned that in addition to emissions from engines, you know, from diesel and so on, that a certain amount of air pollution is caused by cars on roads.
Yeah, yeah.
Yes, I think that the word there is tyres rather than fires.
Tires,
Tyre,
right.
yes, this is the Oslo effect, I believe it's known as the
I think
car tyres.
Oh, this is my webcam effect, I think. So I'm speaking underwater.
Yes, yes, no, tires do wear, they produce particles. Yes, this is included in the, obviously you can get much more detailed breakdowns of sources than I showed in this slide. So tire wear, brake wear, they all produce particles, particularly close to roads. They're particles that do contain some nasties, particularly heavy metals. So yes, indeed.
Yeah, yeah. Any more questions? Anybody got a question they want to raise?
Well, I see that Marion's asked the question of whether the pollution figures for Cirencester refer to just after the B-52 takes off from Fairford or just before. But I was wondering on that sort of subject. You showed a map with fairly high resolution measurements of air quality. Is that actually by going somewhere and taking a measurement, or is there a way of doing it using light from satellites or whatever?
Yes, well, so this is the map of Cirencester, for instance, with roads.
For example.
Yes. No, I should really have said these are not measurements, right? So this is a model. And no, they're nothing like so many measurements, but there are measurements. I mean, I showed some of them from Reading. There are similar stations around the country, local authorities make measurements. These are all put together, combined with meteorology and things like that, to produce a model which gives you emissions for every square kilometre of the UK. So, so they're not measurements. No, I'm sorry.
Okay. But presumably they then have been compared with a few measurements to check that they're in general about right.
Yes, they are pretty carefully controlled. So yeah, quite a lot of effort is put into making them realistic. So, but for instance, they're not likely to pick up like small local sources which don't appear in anyone's pollution inventory because they're
yes, I noticed the Chimera model seemed to show a peak in the morning rush hour and the evening rush hour, and I was thinking, that's interesting, but then of course it's actually just a model, so they are modeling it from the traffic flow rather than indicating that there is traffic flow. Yes,
indeed, but of course the model, once again, it's been validated against measure, and if you measure, there actually is a peak in the morning.
Yeah, which makes sense.
I see there's another question here from Patrick Coleman. Has any measurement been made to your knowledge of the emissions from events such as the RAF International Air Tattoo? That's another specific one, isn't it? Rather like the previous question.
Well, I think quite possibly your local council might make measurements, or certainly if anyone's complained about it, then maybe more national agencies will. It's actually quite hard to measure. I mean, I know from my experience around power stations, trying to detect a power station using air pollution monitoring is actually quite hard. It's partly because they've got big chimneys, so the pollution doesn't come down for at least 15 kilometers. And then, where do you put your monitoring station if the wind is just slightly off? You still won't see the polluted Like you mentioned earlier, Richard, there are you can see NOx, for instance, from satellites and other things. So that would be the best way to do that.
Is there, in fact, a way of using, I don't know, ultraviolet light of a particular wavelength that can identify NOx in the air, or is there?
Well, possibly. I mean, the way it's measured is actually through what's called in the trade a NOx box.
Ah.
It's a little box that measures it's photochemical. So it's but you have to pass the gas through the box in order to do it.
Okay.
I mean, you do get LiDAR systems, for instance. You can measure SO2 with LiDAR, so laser beam that you're shining up and refracting from things. So possibly NOx, I don't know.
You mentioned at some stage that China has made an improvement in the amount of pollution. Would you like to elaborate on that? I know that they are planting huge areas to forest of one sort or the other, but that will take a long time to take effect. But at the same time, they're also installing new coal-powered power stations weekly, almost, certainly monthly. Although I think you indicated that the pollution effect was actually reducing. Is that per capita or what?
Yes. Well, they had a big effort on particulates. Now, they were able to bring it down partly because their older coal-fired stations had very poor particulate control. So, it's very easy to get 99.9% capture of particulates with the right technology. So fitting the right technology, having the money to operate it will get you quite a long way if your pollution is pretty high to start with. So well, they did it. As you say, they're still enthusiastic with building coal-fired power stations. This is good for things that it's hard to remove, like CO2. They now have quite good sulfur control on their power stations, so and even better NOx control than we did on some of ours 20 years ago. So they are trying, but they've also got a huge energy demand from further economic development and a billion people. So potentially it's a big problem.
Yeah. Are there any other questions from anybody?
Well, there's a question there from Neil Cook,
Yes,
which is, if you had to purchase a new vehicle using a fossil fuel rather than electric, which would you choose to produce the lowest emission, gas and particulates, and why?
Yes. Well, I mean, I have driven a diesel for the last 10 years or so, and I did consider its higher NOx emissions, but I did think it also has lower CO2 emissions. Living out in the country, I thought the lower CO2 outweighed the higher NOx. I didn't know about Volkswagen's, and it is a Volkswagen, there's efforts with engine control systems then. Next one, I'll be torn because, partly because I know the diesel emission control technology has got a lot better. Same time, there's Bristol, for instance, is thinking of banning diesels in the centre. And that's part of the London ULZ. So I think next time I might go for a petrol-driven car, not a hybrid. Because hybrid's got a huge weight penalty.
Yes, and there's a follow-on question from Neil. If you choose an electric car, what effect would this have on the gas and particulates from the point of view of the generation of that electricity in the UK?
Yes, right. Well, I mean, the answer is obviously the gas and particulates will probably be generated somewhere else. However, it's not as bad as it would have been because of the increasing penetration of renewables. So there's almost no coal generation left in the UK now. The gas doesn't produce much particulates. Oil is too expensive to burn too much. So particulates, not too bad. There will be a little bit of NOx. So, and the other thing is the power stations have got big chimneys, so the stuff is dispersed much better than it is from your car exhaust pipe. So if you live next to a main road, you are actually imbibing higher concentration. So it's better if you have to emit it from a power station. The power station man talking.
Yes. So there's a question there from Jim Thompson. While the focus has been on human health, could you comment on air quality effects on biodiversity and environmental impacts on wildlife, etc.? I don't know whether that's your field too.
Yeah, yes, it is. Yes, yes, and this is yet another. You could do a whole lecture on this as well.
Yeah, that's the next talk.
But yes, there are effects, particularly of nitrogen emissions, so both NOx and ammonia. I don't know if you notice around in the countryside, you might just notice there are more nettles than there used to be, for instance, and other similar nitrogen demanding plants. Because of this sort of land is gradually increasing its amount of nitrogen. And this is having a deleterious effect on some of the rarer species, because the things that like nitrogen are usually the things, nettles, coarse grasses, that can overgrow everything else. So rare species are tending to decline because of that. So, so this sort of eutrophication, it's very gradual, but it's certainly being seen in, and you can objectively show it in different parts of the UK. I mean, the pollutant gases do have an effect on vegetation as well. When I was starting this, the biggest effect was sulfur dioxide. Trees didn't used to grow in the South Pennines because there was too much sulfur dioxide. They just died. Now you can grow them quite comfortably. And now the biggest vegetation effect is something I haven't talked about, which is ozone. So ozone is having enough of effect in the UK to start changing vegetation composition as well, affecting the yield of agricultural crops. So yes, there's a whole other world if we get away from human health.
Okay, that's interesting. I hadn't really noticed it on nettles, but we've certainly noticed ivy growing more.
Yeah.
Is that a high nitrogen demand?
Yeah, I would guess so. It's the sort of thing that is. Ellenberg categorized all species into nitrogen lovers on a scale of 1 to 9, and the nettles come up at 9. I don't know where ivy is, but you could look it up.
Yeah. Any more questions from anybody? It's a huge subject, so we could go on for some time, but unless there are any other questions, I'd like to thank you on behalf of all members for a fascinating talk, huge amount of data to look at, and I'll be interested to see, Richard, when if we're able to put it up on the website.